This next section is section 8.7, Integration by Tables and Other Integration Techniques. As I said, I think it was 1 or 2 recordings ago, we had 3 integrals that I said this is the beginning of the integration by tables section, which is what we're in right now. So we've seen before that basically once you have something of that form, you can then look through and find the one that matches it best, figure out what the function u is, what any constants, maybe a, b, c, are, and substitute into the formula that's given in the table. So these are all found in Appendix B of your textbook. So you'll want to look in your textbook, whether it's your physical textbook or your online ebook. You can navigate to Appendix B and find all of these tables. And the tables are grouped into all kinds of different sections. The titles of those sections, or at least some of them, is u to the nth, quadratic a plus bu plus cu squared, a sum or difference of 2 squares, a squared plus or minus u squared, the square root of a squared minus u squared, inverse trigonometric functions, logarithmic functions, etc. And so what you'll be looking for is for things in that section and be able to integrate something just by using that as a formula. Now all of these can be verified. Usually something like partial fractions or integration by parts or substitution. These can be proven. There's just kind of a shortcut way of finding an answer to an integral. It does sometimes take a lot of thought and insight in order to figure out which one is the correct formula to use, and it'll often involve a lot of substitution. So, for example number 1, we are to integrate the integral of dx over x times the square root of x minus 1. Since we have the radical, probably we should think of this, since x minus 1 under the radical is linear, we should probably be looking for something that has this basic format, the square root of a plus bu. Okay, and if you look at formula 17 in the Appendix B, we need to think of this as this form, and so we really kind of need to think about what is A, what is B. To write it in that order, we would need to write -1 plus x, where A is -1 and B is, oops, wrote the whole thing there, sorry. B is +1 and u is x, which means that du is just the same thing as dx, and so there'll be no need to introduce a new constant there. And so using formula from number 17, which is du, the integral of du over u, which is what our x is, times the square root of a plus bu, which we've written ours in that form, -1 plus x under the radical. Then, since a is negative, we will use number 17 with a negative. This should be 2 divided by the square root of the opposite of a, so the opposite of -1. Right now I'm going to write everything in as if you can't simplify as you go. And I realize that, of course, you can take the opposite of -1 without having to write that as a step. But this is more for note-taking purposes. so that you have a good sense of where everything went. Anyway, times the arctangent of the square root of a, -1, plus b, which is 1, times u, which is x, divided by the opposite of a plus c. Okay, so this simplifies to be 2 arctangent, or tangent inverse, of the square root of x minus 1 plus c. And that would be our final answer for that one. So again, a lot of it is just finding the right formula and going with it. So let's look at example 2, part A, which is the integral of x squared over 5 plus x. And what I'm going to recommend that you do as I write down each problem is after you have a good look at it, pause the recording and go looking to see if you can find what you think is the form that would fit this in Appendix B. So go ahead and pause and then come back. Well, it looks like this one uses number 6 is the closest match to it. And I'm going to write down the numbers, and obviously you're not going to have these memorized by number. This is just for note-taking purposes so that you can follow what became of what you were looking at. So our u must be x, du is dx, a is 5, and b is 1. And so this is, by number 6, as a formula, 1 over 1 cubed times the quantity, the opposite of 1 times x divided by 2 times 2 times 5 minus 1 times x plus 5 squared ln of the absolute value of 5 plus 1 times x plus c, the constant of integration. So that simplifies to be the opposite of x over 2 times 10 minus x plus 25 times the ln of the absolute value of 5 plus x plus c. All right, so let's look at B. B is the integral of 1 over x squared times the square root of 1 minus x squared dx. Okay, so pause the recording and go look at Appendix B and see which formula you think works for this one. I think it's number 44, where u is equal to x, so du is dx, and a is 1. So, according to number 44, this should be the opposite of the square root of 1 squared minus x squared over 1 squared times x plus c, which further simplifies to be the opposite of the square root of 1 minus x squared over x plus c. All right, part C. This one is cosine to the 4th of x. Oh, I'm sorry, 3x. 3x dx. Okay, well, I see, I'll pause and figure out which one this one would be. I think it's number 51, where u is equal to 3x and du is equal to 3 dx. Okay. And n is 4. By the way, n is also a letter used for constants in this type of problem. Okay, so this would be equal to 1/3 times cosine cubed, because we're reducing that power by 1, n minus 1 is 3, cosine cubed of 3x sine of 3x divided by 4 plus 3/4 times the integral cosine squared u du. And the reason I left that in terms of u was because that's going to be another formula. Now we know how to do this one. We've got the power reducing formula that we could be using there. But what I'm going to do is leave it in that form to go forward. So now this is number 49. And so using 49, oh, by the way, I'm also going to simplify. 3 times 4 makes this 1/12 cosine cubed 3x sine of 3x. And don't forget we're distributing that 1/3. So this will be plus 1/4 times. Now using number 49, this is going to be 1/2 times the quantity 3x plus sine of 3x cosine of 3x plus c, the constant of integration. So our final answer is 1/12 cosine cubed 3x sine of 3x plus 3/8 x plus 1/8 sine of 3x cosine of 3x plus c. All right, so now we're ready for example D. D is the integral of 1 over 1 plus e to the 2x dx okay. So let's see, pause the recording and see which one you think would be best for this one. I'm thinking 84 is a good match, where u is equal to 2x, which means that du is 2 dx oh, and by the way, back on C, I didn't explain it, but we've done it so many times, I just thought maybe you'd know. But let me go back and explain something I forgot to say. Since du is 3 dx, I need that 3 in there. So I have to multiply outside by 1/3. And that 1/3 is what is the 1/3 on the other side, outside of the brackets. I just forgot to say that, and I did mean to say it, I just forgot. So likewise here, I need for it to be 2 dx, so I'm going to multiply by 2 inside and 1/2 outside, which means that this will be of the form 1/2 integral of 1 plus 1 over, plus e to the u, and now we have the du for that u. And so we're ready to go. Okay, so according to number 84, this will be 1/2, because of the 1/2 we pulled out, times 2x minus the ln of 1 plus e to the 2x plus c, which simplifies to be x minus 1/2 ln of 1 plus e to the 2x plus c. Okay, that was D. Okay, so now let's look at E. E is the indefinite integral of x to the 7th times ln of x dx. So pause the recording and see if you can figure out which of the formulas will be good for this one. Well, I decided that 89 was a good one. So I'm going to let u be x. So du is dx. So this time I don't need to insert any constant like I did the 2 and the 1/2 in the example above. And n is 7. And so this is equal to x to the 8th over 8 squared times the opposite of 1 plus 8 ln of x plus c. So that simplifies to be 1/64 x to the 8th times -1 plus 8 ln of x plus c. Okay, so now several of the formulas that you see in the table, the integration tables, have a form where the integral of something is something plus the integral of another thing, which of course comes from integration by parts. That's how those would have been proven when they set about forming these tables. They had to prove them to put them in the table. These are called reduction formulas because they reduce a given integral to the sum of a function like g of x plus a simpler integral. The integral of h of x is supposed to always be better and easier to do than the integral of f of x was to begin with. So let's do one like that.